Okay, hello guys. Today I'm gonna be solving two problems for you in two different videos, and we're going to see how we can calculate deflections in beams by using the double integral method. Double integral method, basically what we're doing is working with the moment curvature relationship. And if you remember from mechanics of material, the moment curvature relationship says that d squared v dx squared is equal to n divided by ei, where this is the deflection, this is the x distance. And at the same time, if we do the integration of these in both sides, then we can get that, let me see, doesn't look like it's zoomed. Okay, if you do the integration in both sides, then you can get here the slope, which is just dv dx, is going to be the integral of this plus a constant. Remember, this is the slope. And if we integrate this again, then we get that the deflection is going to be the double integral of n divided by ei dx squared plus c1x plus c2. And this is the equation for deflection. Now, of course, we have two unknowns here, two constants. And those constants, we can handle them and we can find them just by using the boundary conditions, which is what we're going to do. Well, let's start with the example. And the first example that we are going to do today, we have a beam with a fixed support at this end, and we have a distributed loading, rectangular, with a value of 1 kilonewton per meter, and this distance is 5, this distance is 5, and we also know, because of the conditions of the problem are given, that ei is constant. So we have to find, the problem is asking us to do is find the slope and deflection equations. And by equations I mean by any point on this beam. We should be able to find at any point the deflection or the slope. So how do we proceed with this? The first thing that we have to do is find the reactions. And we find the reaction by static means, because this beam is statically determined. You only have three unknowns here. Find the reactions. That's the first thing to do. Remember, reactions for this one, this is just a fixed support. This is going to be AY and MA. And we're going to have also AX, which by the way we know is 0, because if we do summation of forces in X, that's going to be 0. There's nothing else acting in X. Let's call this point A, this point B, and this point C. So we find the reactions. This is a distributed loading. Remember, we assume that we can convert these only for purposes of calculating reactions in one concentrated equivalent load. This is 5 times 1, so 5 times 1 kilonewton. And the location is going to be 2.5 from either end, because it's going to be half of the distance from the base. So if we start doing that, then we can say summation of forces in Y now equals 0. And if we do summation of forces in Y equals 0, we have that AY minus that force that is 5 kilonewton equals 0, or AY equal 5 kilonewton. At the same time, we can do summation of moments at A equals 0, and I select any direction because this is equal to 0. For being positive, I'd rather using this as a positive, so if I do that, this moment in A is going in the same direction, so it's going to be MA minus this force times this distance. Remember, if I put my pin here and I apply, the rotation is going to come in this direction. So it's going to be 5 times 1, remember, this is the force, multiplied by the distance from here up to here, which is 5 plus 2.5. And from here, we can solve for MA equal 37.5 kilonewton meter. There you go. Now we have our reactions. If we have to find the equations for the slope and the deflection at any point, this works kind of the same thing that I explained when you have to draw the shear and moment diagram, that you have to look for those points of interest that I used to call, or discontinuities, if you will. So that's the other thing that we're gonna start looking for. We have to find the points of interest that's using my language, or like we used to do in the shear and moment diagram, or if you want discontinuities. And those discontinuities are no other thing than the same things that we used to look for in the shear moment diagram. Those parts where we're gonna be doing sections that we can use for calculating our requirement of deflection and slope. What are those discontinuity of those points of interest? Well, we have, wherever you have a concentrated load, wherever you have a concentrated moment, wherever a distributed load begins or ends at the beginning or at the end, wherever you have a support, internal support, wherever you have a change on EI, those are all of these parts, stiffness or conditions or cross-sectional area or material properties. All of those are important points that we should look for. In this case, it's really easy to find and to realize that we have basically two discontinuity zones, or two parts that we can make a section. And in this part, if you do the shear moment diagram, remember you used to draw a line here where the load starts, where the load ends, and that defines two regions, this region and this region. So that's basically what we're going to do. I'm going to call this part 1, 1, and this part I'm going to call it 2, 2. 2, 2. Okay, now if we go to the first part, to this part, the part that I call 1, 1, you can make a section here and select left or right. I think it's easier, now that we calculated the reactions, use the left side. If we then want to calculate the reactions, we can use the right side. But I'm going to use the left side because I think it's easier for this case. It doesn't matter what you use. You just have to pay attention to the direction of the X and the direction of the diagram when you do it. So we're going to use this side. If I use this side, I'm going to have something like that. And in this end, I'm going to have my reactions. Remember my reactions, the AY is 5. We calculated before, 5. I'm going to have this moment also equal to 37.5. You remember the units. I'm not going to put the units here, but keep in mind that the units are important and you have to start writing the units very often. So at this other end, if you do a section, remember we're going to have our shear and our moment. And this distance measured from here to here, I'm going to say that is x1. Okay. If we use this cut, I'm going to do now summation of moments. I'm going to call this point at 1 here because this is what I said is the name. So summation of moments at 1 equals 0. Remember any convention that I want to. And if I do that summation of moments at 1 equals 0 here, then I'm going to have 37.5 minus this x1 times 5 in this other direction plus m1 equals 0, or in other words, m1 is going to be equal to 5x1 minus 37.5. That's my first equation for this procedure. Now, if I use now my other section, I'm going to do the other section, and the other section is going to be, or I can work with this one. I can start working with this one. Let me start working with this one first. I'm going to work with this one, and I'm going to apply my moment curvature equations. Remember, this equation that I said here. So if I want to find the slope, which is this one, I'm going to first do the integration of n divided by ei. What I'm going to do is this ei, instead of putting it here because it's constant, I'm going to pass it to the other n just to simplify my numbers and not keep repeating that ei underneath the equation every time. So I'm just going to put it outside. Remember, I'm going to just integrate this because that's going to be my dv dx for my slope. Remember, ei multiplied by this, or slope multiplied by this, is going to be equal to this integral of this minus 37.5, and that is dx. Of course, because this is an undefined integral, we add the constant c1. So we solve for this, and we have the slope is equal to 5/2 x1 squared minus 37.5x plus c1. I'm going to keep this equation here, and I'm going to call that equation 1. On top of that, I'm going to do the integration again to get the double integral, because the double integral is going to give me the slope, or the deflection. So if I do the double integral, then I'm going to get my deflection multiplied by ei also, of course. It's going to be the integral of this plus another integration constant, c2. When I do that, my v is going to be, this is x5 x cubed divided by 6 minus 37.5 x1 squared divided by 2 plus c1x plus c2, and this is going to be my equation number 2. By the way, if I wanted to apply boundary conditions here, I could, but I want to do that at the end of my boundary conditions. So far I have C1 and C2, my unknowns. Now let's keep going, and I'm going to do now my other section. The other section that I say that I was going to do is this section here at 2. Well, here you can do the same thing. I can use this side, or I can use this side. In this case, I think it's easier to use this part of the equation, and that's what I'm going to do. I'm going to use this part of the equation. So I'm going to make the section 2, but in that section 2, for that section 2, I'm going to keep this here. I'm going to keep this here so you can see the section that I'm referring to, this section. I'm going to keep that, and I'm going to select just that little portion of this equation here. This is going to be my section 2. Remember, we have this distributed load here, and that value is 1 kilonewton per meter. And here, when you do the equilibrium, or in order for being equilibrium, this part, we will have a shear and a moment. I'm calling it 2 because that's the way I name this section. And for this particular case, I'm going to measure my x from this direction, right to left, and this is going to be x2. Okay, if we do summation of moments, at 2 equals 0 here, this distributed load, I can convert it in one equivalent concentrated load, and the value is going to be 1 times x2, and the location is going to be x2 divided by 2. So whenever you do that, if I'm here and I do summation of moments with respect to this point, I'm going to have negative m2 minus this force also. This force is x2 multiplied by the distance from this point or from this point, but in this case I'm standing at this point, so x2 divided by 2, and that has to be equal to 0. So m2 is going to be equal to negative x2 squared divided by 2. This is my equation of the moment. What for? Remember, we are looking the equation of the moment. We are looking the equation of the moment because by using the equation of the moment, I can integrate that once and get my slope, and can integrate that twice and get my deflection. So let's do that. I'm going to integrate this for the very first time. If I do that integration for the very first time, what I'm getting is dv dx, and I'm going to multiply that by EI. Remember, we are passing, or I'm passing this EI to this side, which is going to be no other thing than my slope multiplied by EI, and that's going to be the integral of this dx plus one constant of integration. Remember, before we have C1 and C2, so I'm going to call this constant now C3. Okay, C3. When we do this integration, then we have the slope EI is going to be equal to negative x2 squared divided by this, to the third, I mean, this is 3, this is 6, plus C3. That's my slope, and I'm calling this equation 3. And if I do the integration of this again, then I'm getting V multiplied by EI is the integral of this. So it's going to be the integral of negative x2 to the third divided by 6 plus C3 times dx plus a new integration constant called C4. So beware with that C4, that's an explosive. I don't want to be called terrorist by saying that. EI times V equal, this goes to the 4th, is negative x2 to the 4th divided by 24 plus C3 times x2 plus C4. There you go. And that's my equation 4. Now, based on my previous equations and these ones also, 1, 2, 3, 4, we have to find our constant. We have this equation, this equation, this equation, and this equation. But let's analyze what those equations really mean. Okay, let's start with whatever. Let's start with this part first. If I'm using this part here, what do we know about this end? We know that at this end, or for x1 equals 0, my slope here is 0 because this is a fixed support. And if you know the deflection of that fixed support, if this is the beam, my deflection is going to be like that. If this is a load here, my deflection is going to be something like that. But it's going to start from 0 here. There's no slope, so a slope is 0. And at the same time, for x1 equals 0, also the deflection is 0 because this is a fixed support. And with this, I can plug this into here and get my boundary conditions in order to get my constant. So let's start with the first one. For x1 equals 0, my slope is 0. Let's put that into the equation number 1. Into the equation number 1, we have 5 half times 0 squared minus 37.5 times 0 plus C1 has to be 0. So C1 is equal to 0. I like that. And if I get this now, the other condition, and I plug it into here, remember now this is going to be 0. So I know that for x1 equals 0, v at the support, which is, you want to call it VA, you can call it V at A. V at A is going to be 0 also. And then this is going to be 0, 0, 0. And C2 equals 0 also. So you can find that C2 equals 0. Remember, this C2 equals 0 comes from saying 5 times 0 to the third divided by 6 minus 37.5, 0 squared divided by 2 minus C1 is 0. C1 times 0, this is 0 already, plus C2. And because my boundary conditions say that x1 equals 0, v equals 0, this is going to be 0, and that's why you get C2 equals 0. That's for the first two. So I have my first equation for slope and my first equation for shear. Now what can, for shear, no, for deflection. Now what can we say about the other two conditions? For the other two conditions, what can we say about the other end? What can we say about this end now, this part? Well, if I'm analyzing this part, this segment, if you want to call it like that, for the cut 2 that we did, I don't know what is going to be the deflection here because it's free. I can't quantify that beforehand. I don't know what it's at. And at the same time, I can't say how much the slope is going to be here. And I can't say how much the slope is going to be at the beginning, or I can't say how much the deflection is going to be at the beginning. But what I do know is that if this is my beam, and I'm going to study my deflection of that, and my slope for that, the deflected shape of this beam should be something like that. I'm exaggerating, of course. And I don't know how much are these values. But what I do know is that this value for deflection has to be the same one if I calculate it in this direction or I calculate it in that direction. So in other words, my boundary condition here, or my boundary condition, what it says is that deflection calculated following my 1-1 cut, this cut, has to be equal to the deflection calculated by using my 2-2 section. Difference with this, that I'm measuring x in this direction for x equals 5. Remember, x1 equals 5 in this direction, and then this one from this direction for x2 equals 5. I'm measuring in this direction. But when I meet them, the deflection should be the same. What about the slope? Well, the slope is the same also. But be very careful, because this is one of the parts where people mess up really, really, really easy. As a matter of fact, it's one of the parts where people is all the time having the problem wrong, and they don't know why they have the problem wrong. Well, if I'm checking the slope now, look, this is the slope, right? This is the slope at that point, and this is the point that I'm looking for, exactly this point, and this is my slope. Well, keep in mind that the way I set up my problem, I say that x1 is measured from this end to this end, and my x2 is measured from this end to this end. Well, if I see this part, the part 1-1 for the slope in the first part, my x is measured in this way. That means that this is going to be my slope, and this is a negative slope. You see that? Because I'm looking at this slope from this end to this end. However, if I look at my slope from 2-2, yeah, the numerical value is the same, but now I'm looking at this slope from this end, from here to here, and that's going to be a positive slope. So this slope is going to be the negative of the other slope. The magnitude is going to be the same, but because one is coming down and one is going up, the way I set it up, then they are going to be opposite to each other. And this is the most critical point here. Most of the people say the slopes are the same, and they might be, but not in this case due to the way I am using my axis of references to each one of them. So if I do that, I can just set up my equations for the slope, and the equation for the slope, where are my equations for the slope? Here, for the first part. This is my equation for a slope, negative slope 5, 1, 1, and the distance is the same. They don't have to be the same, but this distance is 5 and this distance is 5. So coincidentally in the problem the x is the same x. So this is going to be negative, and this is the value of the slope that I got before, 5 half x1 squared minus 37.5 x1 plus c1, but c1 I calculated as 0, so this is it, and that has to be equal to the slope in the second which is this is equation, what I call equation 1, and the slope is the other equation, equation 3. So this is going to be equal to negative x2 to the third divided by 6 plus c3. There you go. That's what we're going to have here. Now this is equation 3. Remember that what we calculated, it was EI times this and EI times this, but this and this cancel out. So that's why I'm just comparing these two slopes. Now once we have that, we can solve for x1 equal 5 and for x2 equal 5. 5 half negative 5 squared minus 37.5 multiplied by 5 has to be equal to negative, this is 5 to the third divided by 6 plus c3. And then from here I can solve for c3. And c3, if I'm not mistaken, which I don't think I am, c3 is going to be 145.83 periodic. This is going to be a weird unit because remember we have EI on the other side of the equation. So just keep in mind that the units has to be coherent. If you work with coherent units at the end, you're going to have the units that you're looking for. So I'm not going to be worrying about even naming what units are these one. So we have the third constant, and now we're going to do the same thing. With the slope, I don't care if I'm going in this direction or if I'm going in that direction, because the slope is not with the slope, with the deflection. The deflection is the same value. The deflection is negative if it's going down and positive if it's going up, but this is negative deflection from here to here. And it's the same if I look at it in this way or if I look at it in that way. So I don't care too much about what is the value. And my deflection is, what is the sign, because it's the same deflection. And my equations for deflections are my equation number 2, that we calculated before this one. Just remember that C1 and C2 are 0. So what I have is 5, 6. This is from here. 5, 6, x1 to the third minus 37.5 x1 squared divided by 2. For x1 equal 5, that has to be equal to my equation number 4, which is this one that we set up before. Remember, this EI and this EI are going to cancel each other out, so I don't care about those either. So my equation number 4, remember this is equation number 2. My equation number 4 is negative x2 to the 4th divided by 24 plus C3, it says here C3 x2 plus C4, but this C3 is that value that we just got from before. So I put this in here for x2 equal 5, and when we put this here, this x1 and this x1 and this x2 and x2 elevated to all the powers that you have to, you can calculate your constant C4, and the constant C4 is negative 1067.71. Okay, now we calculated all our constants. Summarizing, if I want to just do a compilation of everything that we got from this problem, basically, remember we had this beam at the beginning, and we have to find the slope and deflection equations at any point for this beam. And this is what we got. From A to B, the first part, my slope was 1 divided by EI. Now I have to put this EI here. And the equation that we got for that was this one. And C1 we already calculated, it was 0. So 5 half x1 squared minus 37.5 x1. This is the slope. And if I can continue with my slope now from B to C, my equation for a slope, or better said, from C to B, my equation for a slope is 1 divided by EI negative x2 to the third divided by 6 plus 145.83. That should give me the value for a slope at any point in this beam. Now, if I'm worried about deflection now. For deflection, from A to B, within this part also, the deflection that I got was 1 divided by EI 5/6 x1 to the third minus 37.5 divided by 2 x1 squared. And for CB or BC, I don't care about this, but I measure it in this way, so I should say CB is 1 divided by EI multiplied by negative x2 to the fourth divided by 24 plus 145.83 x2 minus 1067.71. And basically this is what we have to find in this problem. Now, if I want to know how much is the value of the deflection at 4 meters from the support A, deflection, well, then I go here and I put x1 4, and that will give me the value of the deflection at that point. That I want to know what is the value of the deflection here. What is here? 1 meter from here to here. Well, remember, I'm not going to measure 1 meter from here to here because this equation was, well, this equation in this case, because it's from CB, and I didn't measure it from here to here. I measured it from here to here, so I have to put x2 equal 4 from this end to this end, and that will give me the value of that deflection at that point. I hope that you like this problem. This is just a review from Mechanics of Material, and I'll see you in the next video. Have a good day.